All right, I want to talk a little bit more about force. We talked a little bit about it, and I want to go back to that slinky problem for a minute. Now, when that slinky first fell, the force acting upon the slinky was the force of gravity pushing it down. But at the same time, uh, the expansion of the slinky was just because of the coiling effect was causing it wanting to contract back to its normal state. So there was also a force up within the spring of the slinky. So you could see it on the bottom of the slinky where there was, even though the top was falling, the bottom was staying perfectly in place until it has compressed back to its original state of being a slinky, and that upward force disappears, and then nothing is happening but that downward force. Let's just take another quick look at that. I know we've seen it before, but let's look at it, and you can see, kind of envision these forces as they happen.
So with our conversation about forces, I want to throw something into the mix here called vectors. A vector is just a way that we measure force, and we use an arrow. That's what a vector is. We use an arrow to measure force. So what the arrow does is it tells us the direction of the force, and it also tells us the magnitude of the force. By magnitude, I'm talking about how big of a force is it. If I have the direction going this way with a magnitude force this large, and then I change it just a little, what I did there is I changed my vector so the direction's the same, but the magnitude is about half the amount of force. So when we're drawing vectors, we can sometimes show opposing forces going in different directions, right? And the magnitude will give you an idea of the overall direction that this interaction will occur in. So like if this is twice as much of a force as this, then when they collide, say this is like two football players, they're going to move in this direction because this is a greater force.
Okay, so when we're measuring force, we measure it in a new unit, a metric unit called the Newton, named after this guy right here, Sir Isaac Newton. And you're going to see this pop up quite a bit. I want to show you a little animation that I made, and I know it's not a very good one, but if you watch it, you could probably go to this website and make some yourself. It's called goanimate.com. But here goes.
You're talking about newtons, but I don't really know what a newton is.
A newton is the unit for force.
But what does that mean?
Well, 1 pound is equivalent to about 4.45 newtons.
So, a newton is the same as weight?
Well, newtons are how we measure any force, including weight.
Could I use newtons to measure how much force I push on something?
Absolutely.
So when measuring with newtons, you can see on some scales, if you look at this scale, it says grams for weight on this side. But since weight is a force, it has newtons on this side, so we can measure the force of this weight in newtons. And there's different kinds of scales to do this. Here's another one measuring in newtons. Alright, we could be using these throughout the class.
All right, so let's talk about the next thing here now. I want to talk about force as a weight. And I want to go back to something that you probably heard before, that weight and mass are different. And I want to explain to you how they're different in more detail. So here's a scale that's going to give us the weight of me. All right? So if we look at this in the sense of, how does my mass and my weight change in two different locations, we can get a better sense of what's going on here. So in this case, my weight is how much gravity is pushing down on me. Now, if that's the case, if I'm on Earth, I know that gravity is pushing down on me with an acceleration due to gravity of 9.8 meters per second squared. So here I am on Earth, and I could say 9.8 meters per second squared pushing down on me. So here's where mass and weight become two different things. My mass is just all the stuff inside of me, right? What am I made up of? And I can say there's 77 kilograms of mass within me. Now gravity is also pushing down on all that mass with an acceleration of 9.8 meters per second squared on Earth. So my weight on Earth is taking my mass times my acceleration due to gravity, 77 kilograms times 9.8 meters per second squared, and I get 754.6 newtons. That is my weight on Earth. My mass is 77 kilograms. Now if I go to the moon, there's the moon down in the corner, and here I come. My mass hasn't changed, but the gravitational push on my body has, because the moon is much smaller than the Earth. Alright? So I'm still at a mass of 77 kilograms because I brought everything that was a part of me with me. All 3 fingers on both hands are there. But the gravity on, oh, I'm sorry, a little typo here. I shouldn't say Earth. The gravity on, cross that out, the moon, there, I'll do a little editing. There we go. The moon is 1.62 meters per second squared compared to 9.8. It's way less. So I do the same math. My weight on the moon is my mass, 77, times the 1.62 meters per second squared, the acceleration due to gravity on the moon, and I get 124.74 newtons. Quite a bit different. So that's dealing with the force of gravity and how it affects weight and how it's different from mass. But we're not just dealing with the force of gravity all the time. We also can deal with forces pushing on objects or pulling objects. So in this case, I'm dealing with a force, let's say, of 20 newtons, and there's my vector showing the direction of the push on this box. Now you would assume that that box is going to start moving, especially if there's nothing too heavy in it, right? But if I have an opposing force of 60 newtons pushing in the opposite direction, now I have 2 forces working on each other. And this is where vectors come in handy. You can see the difference in size, the difference in direction. What we're going to have is a very simple math problem here. 60 minus 20, an overall force of 40 newtons in the direction going to the right. All right? We refer to this as the net force. Right? It's the sum of all the forces. You take the 60 in one direction, subtract the 20 in the opposite direction, we have a total of 40 newtons in one direction. That's referred to as the net force. So in this example, we also have a net force of the friction on the floor pushing on his feet and his feet pushing backward. The overall force is greater of him pushing backward, so the net force is in the right direction. And we call this an unbalanced force because one force is greater than the other, giving you an overall net force that is greater than 0. Anytime you have a net force of 0, that means you are not unbalanced, you are balanced. You have a balanced force. So a balanced force is what we also refer to as something being equilibrium. When you have a balanced force, or you're in equilibrium, your net force is 0. So here we have sled dogs pushing or pulling in opposite directions with the same amount of force, 200 newtons of force. So the net force is 0. The sleigh in the middle does not move. So this sleigh in the middle is at equilibrium. So anytime you see something that is not moving, its net force is 0. It's at equilibrium. But you can also have a net force of 0 with something that is moving if it's moving at a constant velocity. Go back to the example that we talked about with skydiving. As you speed up and you're accelerating, you have an unbalanced force. But eventually when the air drag, the air resistance pushing upward becomes equal to the gravity pushing downward, and you've reached terminal velocity, you don't speed up anymore. You keep going the same speed that you all the way until you pull the parachute, which might be 125, 135 miles an hour. But your overall speed does not change. You have 2 forces acting on you that balance out and has a net force of 0. So you can be moving at a constant velocity and have a net force of 0 as well. So to go along with what we were just talking about a little bit more, I have a bowling ball and just a little blow-up globe. And when they're both sitting here trying not to move, they have a net force of 0. And there's a special quality that objects have. If I could personify, I'm using an English term here, right? I'm going to give this ball personality for a moment. When it's sitting here not moving, it doesn't want to move. Right? It has no desire to move at all. That's called its inertia. The inertia of this ball sitting here with a net force of 0, motionless, it wants to stay motionless. It will continue to be without motion until some sort of outside force pushes on it. Now the same goes for this ball. All right? The difference being is this one has more inertia because it's more massive. This one has less inertia because it's less massive. So I could do this, no problem, because it has such low inertia. This one, I can't. It has a lot more inertia. So the same thing applies with the object when it is moving. When the object is moving, it wants to continue moving until some sort of outside force stops it, until a net force stops it. And being that this has very little inertia, it doesn't take much to stop it. This one, having a lot of inertia, takes a lot more force to stop it. Ready? Watch this. Are you sick? Did you really want me to do that? That's messed up. This idea of inertia is something that Sir Isaac Newton really hit upon when he started discussing his ideas of motion, the laws of motion. And he summed it up in his first law of motion, often referred to as the law of inertia, Newton's first law of motion, which goes something like this.
An object in motion stays in motion, and an object at rest stays at rest unless a net force acts on it.
Word. So here it is again. Here's what Sir Isaac Newton said. You might want to pause this so you can write this down yourself. Otherwise, I want to move on to the next piece here. I have two problems that I want to deal with in class, and I want to introduce them to you here in the lecture. Both of these are dealing with Newton's first law. Problem one, the chimney brick dilemma. When you're putting new bricks into a chimney, you need to get bricks up high, so we use a pulley system. Now the dilemma we have is how much weight do you have to use to pull up the bricks? I want to introduce the dilemma to you here in a video clip showing you how you'll set this up in class.
Here's the whole system set up. You see the pulley set up. We'll follow the strings down. This one that I'm holding represents your body weight, and this one on the ground represents the bricks that are going to be picked up. So what I'm going to need to do is let go of this one to see what happens to this one. But before I do that, I want you guys to try this in class and experiment with it yourself.
And the next problem is dealing with where to park on a hill. Is it best to park at the top of the hill, in the middle of the hill? Where will you experience, or where will your car experience the least amount of force pushing it down the hill? And once again, here's a little video showing how we'll do this in class.
The next problem we're going to investigate in class is parking on a steep hill, as you saw in the picture there. And the question is, does it matter where you park if you're on a slope? Say you have like a 30-degree angle, something about like this board here. Does it matter where you park? We're going to use these little cars right here. They have wheels on the bottom. And we're going to see if a car parking at the top of a hill versus somewhere in the middle of the hill, if it'll affect how much force is pushing the car down the hill. Alright, so I have just a regular egg here. It hasn't been boiled. And here I have an egg that has been boiled. Alright, now I want to show you something. I'm going to spin this and stop it. Take my finger off. Let me do that again. Alright, and it stops spinning. I'm going to take the egg that has not been boiled. It's a little harder to spin, but when I stop it and take my finger off, it continues to spin. Now, the question is, what's going on here?
So if we could take a look at the inside of the egg, here's what's happening. Once again, we have inertia in effect. I spin that egg, and the yolk on the inside spins with it. But when I stop the egg, that yolk on the inside keeps spinning, causing the egg to start spinning again when I let go.